Good day to everyone. In this lecture, we're to discuss the last part or the last step under the four-step forecasting model, which is traffic or the route assignment.
So the traffic assignment, also known as the route assignment or the route choice, basically is the last step in which we assign or determine which route is the best to be used by our trip makers. So this assigns the precise traffic flow to specific routes. So this would now require us the construction of the mathematical relationship linking our travel time to the traffic flow along the routes. So in simple approach, we assume that a linear relation between travel time and speed will occur, assuming that there is a free flow condition in our routes. The travel time is assumed as an independent value of our volume, while a complex approach of the traffic assignment would now assume a parabolic speed-flow relationship. So the time would increase more quickly as traffic flow reaches its capacity, and the travel time would be dependent on the volume. So basically, the complex approach will be more realistic compared to our simple approach. So the assumptions that we would make or that we will take if we are performing the traffic assignment in our forecasting would be: 1. The trip makers would choose a route that would connect the origin and the destination with the shortest travel time. Also, the trip makers always know the travel times on all available routes between the origin and destination. So what does it mean? So basically, these assumptions are more or less not ideal kasi hindi siya ideal kasi mas realistic siya. So ikaw, probably you are always using these assumptions when you are going to choose the route you are going to use. So let's go back when you were still attending the university nung wala pang pandemic. So the trip maker, ikaw na trip maker, basically, ang pipiliin mo na route para makarating ka sa school para hindi ka malate will be the shortest travel time. So will you take for me, for example, ako bumababa ako sa may patriotic. So kung ako ang papapiliin, saan ko mas pipiliing dumaan? Doon ba sa may gate gate 5 sa may malapit sa hospital, pag doon ako sa patriotic bumaba, o doon ako sa main gate? Siyempre, ang pipiliin ko will be the shortest travel time, which is nearer on from my origin, which is the route papuntang gate 5, which is the gate near the hospital or near the dormitory. So that's number 1. Also, as a trip maker, I must know or I will know where are the or which of all the available routes will have or the times that the routes will have. So if I have route 1, for example, alam ko na 10 minutes ang biyahe doon. Route 2, alam ko na ang travel doon is 50 minutes. Route 3, ang travel doon is 3 minutes. So basically, alam ko kung kailan or sa ano yung pipiliin ko based on the travel times and the situation on that route or that traffic choice. So the methods now in performing traffic assignment would include the user equilibrium, wherein we apply the word drops principle or an all or nothing algorithm. And the next method is the system optimization, in which we follow this equation wherein S of x is now equal to the sum of x sub n times t sub n times t sub n, which is a function of x sub n. So the first principle for traffic assignment that we use is the word drops principle. So in here, the individuals cannot improve time by unilaterally changing routes, assuming the transportation network is at equilibrium. So the travel time between specified origin and destination on all used routes is the same and is less than or equal to the travel time that would be experienced by a traveler on any unused routes. So in here, so basically, ang sinasabi sa Wardrop's principle is that even if we have several routes or choices to use in going to our destination, we assume that in Wardrop's principle is that all of the choices or all of the routes will have the same time that will take us to our destination. So kung sa first route natin, it will take us 5 minutes to arrive at the destination. So same goes with the second, third, fourth, and other route choices. So basically, example nito, so kahit magsaysay or Bonifacio, for example, ang pipiliin natin to go to the university, dadating pa rin doon sa school at the same time, 5 minutes at the same time. So basically, kahit na ano ang piliin mo, magsaysay or Bonifacio, darating ka pa rin on the same time. O kaya, malilate ka pa rin in the same time. So, traffic sa Bonifacio, kaya nagmagsaysay ka, pero ang dating mo will still be the same. So, that's how Wardrop's principle works. So, this is also known as the all or nothing principle. So, it means if travel time is assumed independent of the volume, all trips are assigned to a route of minimum time and cost. So, ibig sabihin, sa all or nothing, if we have, for example, 2 routes to choose from, ang pipiliin natin will be the route with the least time to arrive or the minimum cost na makarating doon sa destination ninyo. And in choosing your routes, the volume now that passes through the 2 route choices are independent. So, it does not affect your choice. Kasi sa all or nothing, ang mag-a-affect sa choice mo will be the time or the cost of travel. Okay? So, to understand the Wardrop's principle, let's solve an example. So, let's say we have 2 routes that connects a city and a barangay. And during peak or morning commute, there are a total of 4,500 vehicles that would travel using Route 1 and Route 2. So this will be our total volume that will be distributed in Route 1 and 2. So given now, for each route, we have a speed of 60 for Route 1, and for Route 2, there will be a 45 miles per hour speed. And the distances between the city and the barangay, if you use the Route 1, will be 6 miles, and for Route 2 will have a distance of 3 miles between city and barangay. And then we have here the travel time for Route 1. Using Route 1 is 6 minutes, and the time of travel now using Route 2 will be 4 minutes. So we'll have now T1 will be our travel time on Route 1. T2 will be the travel time on Route 2. So this one. So note that the travel time on Route 1 increases 2 minutes for every additional 500 vehicles added. So there's a condition when choosing Route 1. So when we choose Route 1, again, it means that for every 500 vehicles added, there is an increase of 2 minutes for the travel time. So ibig sabihin, so let's say 500 vehicles, it's 6 minutes, so additional 500, so you add 2 minutes. So that's how what happens when you use Route 1. And then for Route 2, the travel time now will increase with the square of the number of vehicles expressed in thousands of vehicles per hour. So in Route 2, whenever the number of vehicles now increases, the time will also increase with its square. So to solve this, now we will use our travel time by user equilibrium and system optimization, which is under Wardrop principle or the all or nothing principle. For this problem, to understand now the scenario, so we have here a total of 4,500 vehicles that would be coming from our origin, and they will either choose Route 1 or X1 and Route 2 or X2 going to our destination. So basically, whatever comes from the origin will also be the same value that will arrive in our destination. So let's assume that x1 will be the vehicles that will be choosing route 1. So these are in thousands of vehicles per hour. Then we'll have x2, which are the vehicles choosing route 2 in thousands of vehicles per hour. So for our equations, as it was given or stated in the problem, so we'll have now 4.5, so that will be equivalent to, so 4,500 vehicles is equal now to x1 plus x2. And that for T1, this can be written as 6 plus 2 divided by 500 times 1000 times x1, or that's simplified as 6 plus 4x1. So from the problem, every 500 vehicles passing or that is added will be an increase of 2 minutes. So 6 minutes plus 2 for every 500 vehicles. So we multiplied 1000 since our value is always in vehicles per hour. Okay. So next we have for T2, that will now be equivalent to 4 plus the increase will be in terms of the square of all the number of vehicles passing or choosing route 2. That's now 4 plus x2 squared. So this will be our two equations. So from here, 6 plus x1 is for T1. We have 4 plus x squared for T2. And we know that x1 plus x2 is equal to 4.5. So we could simply equate our values in terms of x1 and x2. So for the first part of the problem, we want to apply or solve the time of travel in terms of using a all or nothing method. So for this, we first assume that all the vehicles or all traffic will choose route 1. So if that's the case, then x1 will be 4.5 and x2 will be equivalent to 0. So substituting the value of x1 in the equation of t1, so that will be 6 plus 4 times 4.5, which will give us a value of 24 minutes. And t2 now will be equivalent to 4 plus x squared, or 0, that's equal to 0 now. So t2 will be equivalent to 4 minutes. And then, once we have performed all or nothing for route 1, we also apply this using route 2. So using route 2, so x1 now will be equal to 0, and then x2 will be equivalent to 4.5. So with this, we'll have t1 is equal to 6 plus 4 times x1 equal to 0, giving us t1 equivalent to 6 minutes. And t2 is equal to 4 plus 4.5 squared, or giving us a value of 24.25 minutes. So if you can see, if all vehicles now will be choosing route 1, there will be more time travel for T1. Thus, if we assume that all traffic is using route 1, then as a additional user, you'll be choosing now the shorter time, which is route 2. Same goes if all traffic chooses route 2, as an additional user, you will be choosing now a shorter period of travel, which is T1, which is at route 1. So that's for all or nothing. So since the assumptions now uses either of the two routes, then T1 is equal to T2. So with this, we'll now equate our equation. 6 plus 4x1 is equal now to 4 plus x2 squared. And we know that x plus x2 is equal to 4.5, so we could substitute our values in terms of x1 or x2. So in here, we now use in terms of x2. So 6 plus 4 times 4.5 minus x2 is equal to 4 plus x2 squared. So simplifying, we'll now be able to get a value of x2, which is 2.9 in terms of thousands vehicles per car, or that's equivalent to 2,900 vehicles. Or x1 now will be equivalent to 1.6, or that's 1,600 vehicles. So this is now the distribution or the traffic assignment. So in here, it means that if we're going to apply the all or nothing route, 2,900 vehicles should use route 2 and 1,600 vehicles should choose route 1. So this will be applied if and only if we choose route 1 but the shorter time is the other route, or if we choose route 2 and the shorter time will be the other route. But if what will happen if, for example, all traffic is in route 1 and the shorter time will be T1, and then if we move all our traffic in route 2 and the shorter time will still be T1, then it means that the routes that will be used will only be route 1. So no need for this solution. Okay? So with this, we could now substitute now x1 in T1. So T1 now will be equivalent to 12.4 minutes, which is also the same as T2. So if we distribute our vehicles in our traffic routes, in these routes, they will have the same time of arrival. So by system optimization, we now follow this equation. So this is summation. This is the sum, or s of x, a function of x, is now equal to the sum of x times t. So if you could remember, from all or nothing, we were able to take or derive the equation for t1, which is 6 plus 4x1. So 4x1 came from 2 divided by 500 times 1000. Okay? And then this is x2 times t2. So if we're going to simplify this one, s of x now is equal to 6x1 plus 4x1 squared plus 4x squared plus x2 cubed. So since we know that x1 is equal to 4.5 minus x squared, we could substitute the value of x1 in this expanded equation. So simplifying this one will arrive at this equation. So in order to solve for x2, in which we want to solve for the maximum or the minimum value. So from your derivative, maximum minimum will be equivalent to 0. So in this equation, so by derivative, so it's equal to 0. So what we have attained here is a quadratic equation. So therefore, x2 now will be equal to positive 2.467 or negative 5.134. So we'll be taking the positive value of x2. So x1 now will be equal to 2.033. So substitute x1 in t1, we arrive at t1 equal to 14.13 minutes and t2 is 10.09 minutes. So by summary, in user equilibrium, the vehicle delay will be x1 times t1 plus x2 times t2, which is 55,800. And for system optimization, that will be 2033 times t1 plus t2 x2 times t2, which is 53,613. So if you're going to look at this summary, system optimization basically means that we have optimized our routes, meaning we have used it accordingly instead of being in equilibrium. So we have distributed our vehicles in the different routes in which it will be able to arrive in the shortest and will produce the least vehicle delay. So next example. So for the given traffic flow or given data, so calculate the traffic flow on each link of the network using the given data for the minimum time cost path for a 6-zone network. So the next table here is the average daily trip interchange between each zones or your OD matrix. Okay? So for this problem, we have to identify the shortest link, and there are 7 shortest links in our given data. So the shortest link means we only have an end and an origin and an end or a destination. So dalawa lang yung points ng travel, hindi na siya pupunta sa iba pang zones. So we'll have here 1, 2 or 2, 1. So that's one link. Next, we have 2, 3 and or 3, 2, vice versa. Next, we have 4, 5 and 5, 4. Next, we have 5, 6 or 6, 5. Then we have 1, 4 or 4, 1. And lastly, we have 5, 2 or 2, 5. And we also have 6, 3 and 3, 6. So these are our shortest link. So in traffic route assignment, we want to only choose the shortest links in order to identify our route choice. Okay. So once we have found our shortest links, so what we will do is to identify which of the links will contain our shortest link. So we start off first with the first link, which is 1, 2. So basically, we have this one. So another link containing 1, 2 is 1 to 3, zones 1 to 3, from 1 to 3 or 3 to 1. And then we also have 1 to 5. And then we also have 1 to 6. So the links now that would contribute to link 1, 2 are 1, 2, 2, 1, 1, 3, 3, 1, 1, 5, 5, 1, 1, 6, and 6, 1. So next we have link 1, 4. So I identify which of the flows would contribute to this shortest link. So 1, 4. So basically we have 1, 4, 4, 1. So another link that has 1, 4, wala na. So the only link that would contribute to this link is 1, 4, and 4, 1. So we have the next link is 2, 3. So from this table we have 2, 3 or 3, 2. We also have 1, 3 and 3, 1. So we also have 1, 6 and 6, 1. We also have 3, 4, 4, 3, 3, 5, 5, 3. So this will be the summary of the links contributing to the flow in from zone 2 to 3. So next we have 4, 3, 6. So that will be 3, 6 or 6, 3. So you have 1, 6 to 6, 1. And no more. So we only have these links that would contribute to this short link. And then we have 4 to 5. So 4, 5. We also have 4, 2 and 2, 4. So we also have 3, 4, and 4, 3. Then we also have 4, 6, and 6, 4.
Yes.
Next link, we have 5, 6.
Okay.
So we have 5, 6, 6, 5. We also have 4, 6, 6, 4.
No.
And we have 2, 6, 6, 2. So to summarize, the link contribution for each of the shortest link in our 6-zone study area. So for link 1, 2, contributing links will be 1, 2, 2, 1, 1, 3, 3, 1, 1, 5, 5, 1, 1, 6, and 6, 1. Then for link 1 to 4 is 1, 4, and 4, 1. 2, 3 will have 1, 3, 3, 1, 1, 6, 6, 1, 2, 3, 3, 2, 3, 4, 4, 3, 3, 5, and 5, 3. Then for 2, 5, we'll have 1, 5, 5, 1, 2, 4, 4, 2, 2, 5, 5, 2, 2, 6, 6, 2, 3, 4, 4, 3, 3, 5, and 5, 3. Then for 3, 6, we'll have 1, 6, 6, 1, 3, 6, 6, 3. And for 4, 5, we have 2, 4, 4, 2, 3, 4, 4, 3, 4, 5, 5, 4, 4, 6, 6, 4. And lastly, for link 5, 6, we have 2, 6, 6, 2, 4, 6, 6, 4, and 5, 6, 6, 5. So to compute now for the traffic flow in each of the links, we'll be using table B, which gives us the volume of traffic for our interzonal trips. So for link 1, 2, the contributing links will be 1, 2, 2, 1, we have 1, 3, 3, 1, 1, 5, 5, 1, and 1, 6, 6, 1. So from these highlighted numbers, we simply add them up. So the total length or the total flow for link 1, 2 is now equal to 250 plus 300 plus 100 plus 150, 150, 100, 75, 150, which is now equal to 1,275. So this is the total flow for link 1 to 2. Next, for link 1 to 4, so we still use table B. So contributing link is 1441. So we simply add them up. 125 plus 200. So the total flow for 14 is 325. So same goes for link 23. So table B. So we look for 1331. We also have 2332. Then we have 1661. Then we have 4334. And we have 5335. So adding them up, the total flow now in link 23 is 1,450. And then for link 2 to 5, so we have 1551, we have 2442, 2552, 2662, 3443, 3553. So the total volume now or traffic flow in link 2 to 5 is 1,975. And then for link 36, so we'll have 1661 and 3663, giving us a total flow for route 3 to 6 is 645. And then for link 45, we have 2442, 3443, 4554, and 4664, giving us a total flow for route 4 to 5 as 1450. And then for the link 5 to 6, the traffic flow now in our links will be 42662, 4664, 5665. So add them up, we get a value of 10,000 or 1,025. So once we have computed for all the total flow for our shortest link, then we can simplify now our values or simplify our representation by a diagram. So the link volumes now that would arise from all or nothing traffic assignment procedures. So we'll have 1, 2, 2, 3. So for 1, 2, we have computed a total flow of 1,275. Then we have for 2, 3 is 1,450. This is what we have computed. So next we have 1 is to 4. 1 to 4 is 325. We have 2 to 5 is 1975. Then we have 3 to 6 is 645. Then we have 4 to 5 or 5 to 4 is a total of 1450. And then 5 to 6 or 6 to 5 has a total flow of 1025. So this is now our traffic assignments. So basically, once we have computed for our trip distributions, the distributed flow now will be assigned to a certain route. So for these distributions, all of our distributions will be again distributed in terms of its route. So there are 1275 vehicles that would be using route 1 to 2, and those vehicles that are passing routes 1 to 2 are those that would be traveling from 1 to 2 or 1 to 3, 1 to 5 or 1 to 5, 6 or 1 to sorry.
Ay, bakit yung fit?
So 1 to 5, 4. Okay? So that's it for
So thank you for listening. That is all for the last step, the last submodule for first step forecasting.